Lesson 15, Pneumatic Systems and Fluid Dynamics. We're going to start this discussion with the difference between laminar and turbulent flow. First off, fluid dynamics is the study of fluids in motion, and viscosity is a measure of the resistance to flow. So a substance like maple syrup has a high viscosity. And whereas we can compare that to water, which has a lower viscosity. Factors that affect viscosity are laminar flow. Laminar flow is defined as fluid flow in which adjacent regions of fluid flow smoothly over one another. So if we imagine the regions of flow are all flowing uniformly, this results in very smooth, very uniform flow. If there's any irregularity in the surface in contact with the fluid motion, its particles interact with the irregularity, and this will disrupt their otherwise smooth and straight line motion, resulting in chaotic paths for the particles known as eddies. So we have the same liquid flowing through the same container, but here we've put this small little disturbance inside, whether it's a particle or an imperfection in the pipe. And as a result, this is going to cause these irregular disturbances in the fluid flow, and these irregular disturbances are called eddies. If there is no uniformity in the flow of the liquid, we say there is turbulent flow. Turbulent flow is defined as fluid flow in which a disturbance resists the fluid's motion. You may have heard of turbulence, especially if you've flown in an airplane. Turbulence is a sudden, violent shift in airflow. If ever you've flown through turbulence in an airplane, the chaotic motion of the air particles is obvious as the air currents jostle the airplane on all sides and will affect the lift of the wings and the ability of the pilot to control the flight. Most times when pilots encounter turbulence, it doesn't result in a very large disturbance, though you'll feel the plane moving up and down under severe conditions, which rarely happen in commercial air flights because pilots know how to navigate past or around turbulent airflow. Otherwise, a plane could technically drop 30 meters if ever it encounters severe turbulence. Aerodynamics is another application of fluid dynamics. Cars need to be aerodynamic. That means that the fluids that flow past them, mainly the air, while you're driving, needs to flow smoothly over the car. This results in vehicles that are efficient. So when designing vehicles, engineers will seek to make vehicles streamlined as possible with a smooth shape from front to back, smooth body surfaces, and as few irregularities on the body as possible. Vehicles like pickup trucks generate a lot of turbulent flow because they're essentially like square boxes that are traveling through the air, and this is one reason that pickup trucks have poor fuel economy. There are times when turbulence is actually desirable. Despite laminar flow being desirable in many situations, turbulent flow is also has its uses. For example, when constructing a heating or cooling coil, turbulent flow within the coil results in more efficient heat transfer, as there will be more mixing of the fluid in the coil due to all of the eddies that are produced. If the flow of the coil were laminar, it would be difficult to heat or transfer to or from fluid in the middle of the tube, making up the coil. So turbulence in this case can improve efficiency of a heating coil. A very important concept in fluid dynamics is Benoullis Principle. And Benoullis Principle states, where the speed of the fluid is low, the pressure is high. And where the speed of the fluid is high, pressure is low. So this is an important statement for you to remember or even memorize. It sometimes sounds a little contradictory, but it's actually very true, and it explains most of the features that you'll encounter in fluid dynamics. So, whenever water moves slowly, and think about a large garden hose in which water moves slowly. Whenever water moves slowly, the pressure is high. And when water moves quickly, the pressure is low. So, low speed, high pressure, high speed, and I'll write that down, low speed, high pressure, high speed, low pressure. So here we have a manometer that shows us this exact system. So these are all open to the atmosphere. And the fluid inside is going to move really slow when there is a large area for them to travel through, and faster when it's forced through a smaller area, and then again slow. So whenever there is slow speed, there is high pressure. And whenever there is high speed, there is low pressure. And you can see that as the pressure changes in these openings here. So just remember, high speed, low pressure, low speed, high pressure. Now, this actually has created an understanding of how airplanes work and was able to predict that airplanes could fly if you were conscientious of how to design the shape of the wing. So, just look at this diagram here. We have a wing, and because it's shaped like this, we have low pressure up top, and that's because the wind moves at high speed over the top of the wing, and below the wing we have low speed and high pressure. Whenever this happens, whenever you have high pressure and low pressure, there's always a force that pushes from high pressure to low pressure. Imagine if two systems are beside each other, one is high pressure and one is low pressure, the high pressure will push or move towards the low pressure. So when this happens, the low pressure above the wing and the high pressure below causes a force to push up on the wing, and this is called lift. So the upward force of lift happens because of Newton's third law and Bernoulli's principle. For an airplane, air deflects off the bottom of the wing. The wing exerts a downward action force on the air, and the air exerts an upward force on the wing. Also, pressure above the wing is low and pressure below the wing is high. So the pressure difference adds to this lift. Bernoulli's principle was also can be used to explain the phenomenon of a curveball. A curveball is a way to throw a baseball such that instead of traveling in a straight line, it forms this curved path. And the way this happens is air near the ball's surface on the left is dragged along with the ball in opposite direction. This results in slow-moving air and high pressure on the left-hand side. So on the left-hand side, we have slow air, high pressure. And on the right-hand side, we have high pressure, low speed. And this causes the baseball to move in its direction and will curve, will take this path from high pressure on this side to low pressure on this side. Okay, below we have a summary chart comparing hydraulic systems and pneumatic systems. When you're done, I want you to try these few homework practice questions for pneumatic systems and fluid dynamics, and then complete the corresponding LMS quiz. Good luck.